Hello, Chem 213 students, and welcome for our next set of lectures this week regarding amines in Chapter 22. This is going to be the last chapter of the textbook that we cover, that is reactions. At this point, we're going to be fully prepared to going into describing biological chemistry and biological reactions, having studied the reactivity of all functional groups in organic molecules. And so let's begin to talk about amines. So an amine is basically a functional group where there's a nitrogen atom present. And like a lot of the nomenclature that we've used in the past, there's an indication of primary, secondary, or tertiary amines, although the nomenclature works differently for amines than it did for some other functional groups. When we talk about a primary, secondary, or tertiary amine, we're not talking about the numbers of carbons attached to the carbon that is attached to the nitrogen. We're talking about the number of carbon atoms directly attached to the nitrogen itself, and that's going to be what affects the chemical properties of amines the most. And so that's why our designations here are a little bit different. So for example, in the past, if we would have had, let's see, so get this pen going. If we would have had a alcohol like this, we would call this a secondary alcohol because the carbon that is attached to the hydroxyl group is itself attached to two other carbons. So we would call this a secondary alcohol. So this works a little bit different for amines. What we're interested in when we do this designation here is how many carbons are directly attached to the nitrogen atom in the amine. And so if we have one carbon atom attached, of course indicated by this R group here like usual, we would call this a primary amine if there's one carbon and two hydrogens attached. If there are two carbons and one hydrogen attached to the nitrogen, we would call this a secondary amine. And if there are three carbon atoms attached to the nitrogen atom, we call this a tertiary amine. And of course, the nitrogen with three hydrogens attached is ammonia, which is the common name. Amines, they are ever present in biology. You're going to find them all over the place. You may have heard of the nitrogenous bases in DNA. We're going to study that a little bit later. Those have lots of amines in them, lots of nitrogen atoms, lots and lots of alkaloids, which are generally various types of drugs, including cocaine, caffeine, morphine, nicotine, all containing nitrogen atoms. In general, if you see the "ene" at the end of the common name of a drug, that is indicating that it has an amine group in it. And these are called alkaloids because, as we've discussed way back in Chem 212, nitrogen atoms very readily accept protons. They behave as bases. Their lone pair can go out and grab a proton, and that's going to be really, really important to the way that they react chemically. Some other important naturally occurring amines, adrenalines, see that "ene" at the end indicating the presence of an amine. So this is adrenaline, noradrenaline, which regulates heart rate and dilates air passages, and dopamine, a neurotransmitter that regulates motor skills. And of course, a lack of dopamine in the brain causes rather Parkinson's disease, or is the cause of Parkinson's disease. So one of the key chemical reactivity ideas for a amine is that it will accept protons. The pKa of amines themselves is extremely low. For ammonia, for example, being pKa of 38, they do not lose protons very readily, and instead, in fact, they gain protons quite readily. So if you expose a nitrogen to any acid, it's going to undergo a proton transfer with that acid, and so we see a proton transfer here. This lone pair of the nitrogen grabs the proton, and of course the proton leaves without any electrons, so both the electrons in this bond to chlorine are left behind, and we get what's referred to as a quaternary ammonium salt. The nitrogen being quaternary because it's making 4 bonds rather than 3 here. We obtain an ammonium salt basically here, and we have I wouldn't say quaternary, I guess it's not 4 carbons, but there's an ammonium salt here with the positive ion being the protonated amine, and the negative ion being the chloride ion. Now, nitrogen can also behave as a nucleophile. So it's a pretty decent base. It's a pretty decent nucleophile. Not the strongest base, not the strongest nucleophile, but pretty good. And so here, if we have a primary alkyl halide, for example, we can have a nucleophilic attack on the carbon. Remember that in terms of the electron density here on an alkyl halide, that electron density is being pulled towards the chlorine, making this carbon partially positive, while the chlorine is partially negative. And so that partially positive carbon is attracted to the electrons in the lone pair here in the nitrogen, which are donated to the carbon here to create this bond, and then these electrons here leave with the chlorine as it is the leaving group. And here we get a quaternary ammonium salt, where we have a nitrogen here attached to 4 different carbon atoms with a positive charge here and a chloride ion being the counter ion with the negative charge, and so we get an ionic compound here. You can see the reactivity of the lone pair of the nitrogen, and just the fact that the nitrogen itself is quite negative, that region. The nitrogen is it's not the most electronegative atom, but it's among the most, and so the electron density gets pulled towards the nitrogen. Remember, the nitrogen here with the lone pair has a trigonal pyramidal arrangement. So if we look at it straight from the top here, we have the nitrogen sticking straight up at us, and this is going to be the region of the highest electron density, right around where the nitrogen is, because that's the nitrogen being the most electronegative atom among these bonds to carbon will pull the electron density towards itself, and the molecule is asymmetrical, being trigonal pyramidal, and so the electron density is all collected around the nitrogen atom. In terms of the naming of the amines, the IUPAC nomenclature allows for two different ways of naming primary amines. We can name the alkyl group and end it with a YL, and then say amine at the end, and this is very commonly used. So for example, if you watch Breaking Bad, one of the key plot points is they needed ethylamine to turn pseudoephedrine into methamphetamine. So that's what Walter called it. Personally, I prefer the standard, more systematic names, which I'll discuss in a second. I would call this ethanamine instead. I always thought that it was funny that Walter White called it ethylamine, but it is an acceptable IUPAC name, ethylamine. So here, this being the ethyl group, and then this being, of course, the amine part. So we call it ethylamine. Or here we have an isopropyl group, isopropyl. So a special grouping that you should have the name of memorized there. Just remember it's a propyl group, but instead of the group of interest being attached to the first carbon, it's attached to the middle carbon. And we call this isopropyl. Not isopropyl, but isopropyl. There we go. And this is called amine. So we say isopropylamine, or we have a cyclohexane ring here as a branch off the amine, so we could call this cyclohexyl. And this one is amine. Okay, so that's one way to name these. What I think is the superior name, because it allows for more flexibility for complex amines. If you have a complicated amine, you have to name it in this way. So, as I said, although Walter White may call this ethylamine, I like to call it ethanamine. And here this bears out, because if you have a more complicated amine, this is the way you must name it. So it's named similar to an alcohol, but instead of ending with the anol, we're going to end with N-amine. Otherwise, it's no difference really. We have to state where the amine group is. There will be differences if there are other carbons attached to the amine. That's the main unique factor of naming amines. So here, if we're going to name this amine, let's break down how we would do it. First, we're going to find the parent chain with the longest number of carbons that is attached to the amine. Right? The amine is the higher priority group than methyls or methoxys and so forth. And so this main chain here is going to be called hept, or 7 carbons, and then an, because there's no double bonds, otherwise we'd say ene, amine, heptanamine. So that's the name of the chain, and then what you'll notice here is that we have a couple of chiral carbons. So this carbon here, where the amine is chiral. It's attached to 4 different groups. This carbon is chiral. This other carbon is not chiral. You should know why, right? It's because it has 2 of the same group attached, methyl groups. So we have 2 chiral carbons here, so that's something we're going to have to deal with in terms of assigning R and S. Okay, and we've got here the amine group. So actually, in my circle, I really should have included the amine part as well. So let me fix that circle. So this part is the hexanamine, okay, or heptanamine rather, with 7 carbons. And then in terms of numbering, we're going to want to number in the side that's closest to the amine group. So we're numbering here from the left, 1, 2, 3, 4, 5, 6, 7. And so we've got 2 methyl groups, one on the 4th carbon, so I'll circle these in blue. We have 1 methyl group on the 4th carbon, 1 on the 6th. So this is going to be 4, 6. Oh, whoops, no comma there. 4, 6 dash. Remember to separate the 2 numbers here with commas and separate the numbers from the letters with dashes as usual. So we'd say 4, 6 dimethyl. And then this is for our heptanamine. We're going to say what number that the amine was on. It's on the 2nd carbon. So we call this 2-heptanamine. So we're putting together all the pieces now. The last part is we're going to have to figure out on the 2nd carbon and the 4th carbon, we're going to have to figure out what the stereochemistry will be. And so I'm going to break this down now. We've got the NH2 group here. This is going to be the priority 1 group, having the highest the highest molecular mass. There is a hydrogen here which isn't drawn in, so I'll draw that in here. This one is going to be priority number 4. And then for our other groups here we're going to have a carbon, and at the 1 position, at the 3 position, we also have a carbon. And so we're going to have to break the tie here with the carbon atom. So this carbon atom has 3 hydrogens attached, HHH. This carbon here, again, we count, remember, away from the group. So if we count away from the group, this has 1 carbon, and then it has 2 hydrogens. So this one would be attached to, this carbon would be attached to a carbon, a hydrogen, and a hydrogen. Since carbon beats hydrogen, this is going to be position number 2, this is going to be position number 3. And now we have our group 4 in the back, and on all of our groups set up. This is going to be 1 and 2 and 3. 1, 2, 3. This is going to be a right-hand turn, so this is going to be R. Okay. And then now we have to look at carbon number 4 here, so I'm going to put that over out here. And so in this one, we're going to have a wedge here that contains a hydrogen. It's not drawn, but there is a wedge here with hydrogen. There's going to be a dash here that contains the methyl. So my hydrogen is going to be my priority 4 group here. Now, for the methyl, we've got a methyl and we've got 2 carbons. So we're going to have to compare these. So when I look at this methyl group, this carbon has 3 hydrogens attached. Okay. And then this carbon here has 1 carbon and 2 hydrogens attached, so it's a CHH. And then this carbon over here, carbon number 5 of this carbon here, has also 2 hydrogens and 1 carbon attached. So it will also be CHH. So this will be tied. These 2 will be tied. This one on the dash will be number 3. So now we're going to have to break the tie here with the CHH. And so we go is to the next carbon. So here, this was carbon number 3, has attached to 1 carbon and 2 hydrogens. So this carbon, carbon number 2, is attached to 1 nitrogen, 1 carbon, and 1 hydrogen. So on the second level of comparison, we're going to have nitrogen, carbon, hydrogen. And here on carbon number 6, it's going to be attached to 2 carbons and 1 hydrogen. So we're going to have carbon, carbon, hydrogen. And the nitrogen is going to be the carbon. And so this is going to be priority group number 1, and this one will be number 2. And so to assign R and S, we're going to now have to do the double switch. So we're going to double switch. Remember, it doesn't matter what you double switch as long as the priority 4 groups ends up on the dash. So I'm going to switch 4 and 3, and I'm going to switch 1 and 2, and I'm going to draw a new layout now for this. And the 3 will now be on the wedge, the 4 on the dash, the 2 here, and the 1 here. And so now when we look at this, we're going to have 1, 2, 3. So 1, 2, 3, 1, 2, 3, around in a right-hand turn. This is going to be R. And so now we can write our full name. And so to break down the name, we have on the end, we take this part right here, 2-heptanamine, and that goes right here on the end. And then we put in front of that the 2 groupings here, 4,6-dimethyl. That's going to go right in here. And remember, we always separate the letters from the numbers with a dash. So there's a dash here between the 4,6-dimethyl 2-heptanamine. And then there's going to be a dash before the 4 and 6. And this is where we're going to put our groupings at, our stereochemistry. So on carbon number 2, we had R, so we put 2R. And on carbon number 4, we also had R, so we put 4R. And we separate these with a comma, and we put parentheses around them. And of course, separate the letters from the numbers with a dash. And that constructs our entire name for the amine. So, as you saw, there are multiple names for ways for naming primary amines. If you have a higher priority group, such as an alcohol or a carboxylic acid or an aldehyde or a ketone, these are all higher priority groups than amines. We're going to name the amine as an amino group. So here, the alcohol group is the highest priority. So we're going to have 4 amino, and this should really say 1 butanol to indicate that we have 1, 2, 3, 4 carbons. So 4 carbons, that's where the bute comes. Anol is from the alcohol. 4 amino means that there's an amino group on the 4th carbon. Okay, and so that's what we call it when we have an amine group that is not the higher priority. We call it the 4 amino. Here we can also use para if we have a benzene ring here, so we can call this part here would be called benzoic acid. And then in the para position, we have amino. We could also say 4-amino benzoic acid. That would work as well. And we number it like this: 1, 2, 3, 4. And so, yeah, you use the term amino for the group as a substituent in a molecule that contains a higher priority group. If you have a amine group on a benzene ring, that has its own name, as you recall from the carboxylic from the benzenes chapter. There's lots of special names for substituted benzenes, and the one for the benzene ring with an amine attached is called aniline. And then we can name the aromatic ring as a substituted aniline. And so here we have this whole group part here. This is the aniline, and then at the meta position, there's a chloro group, and so we could say metachloroaniline or 3-chloroaniline would also work. In this case here, we have a substituted aniline again, the amino group being the highest priority group. When we number this, we're going to want to number around in the direction that will get us to our second group the quickest. If we number into going around counterclockwise, we get to the fluoro group at carbon 2, but we get to the ethyl group at carbon 3. So we'd want to number counterclockwise around 1, 2, 3, 4, 5, 4, 5. Whoops, 1, 2, 3, 4, 5, 6. And so again, I'm going to circle in red here this time. This is going to be the aniline right here, right? And so all of this goes into the aniline naming, and then we're going to list the substituents in alphabetical order. And so the ethyl substituent here, ethyl, is going to come before the fluoro in the name because E comes before F in the alphabet. Notice that the ethyl has the higher number, right? But the numbers are only used for the ordering if there's a tie of some kind. Here, so we have, like if you have two of the same groups. So here we say 5-ethyl, so on the 5th carbon we have 5-ethyl, that's this guy right here, and remember to separate the numbers from the letters with a dash, and then we have 2-fluoro for the 2nd carbon here having the fluoro group, and the 5th carbon here having the ethyl group. And again, the ethyl is written first because E comes before F in the alphabet. In terms of secondary and tertiary amines, there are also multiple ways for naming those. For example, very commonly for simple secondary and tertiary amines, what will be done is to simply name the substituents and list them in alphabetical order. So here for this tertiary amine, we have 3 substituents. We have a methyl one. We have here a propyl with 3 carbons. And here we have a ethyl group with 2 carbons. And so ethyl will come first in the alphabet, methyl will come second, and propyl will come third, E before M before P. And so we'll call this ethyl, methyl, propyl, amine. That is a way of naming them. It's a relatively simple name that you can use for simple substituted amines. Here we could call it, here's this an ethyl group. This is also an ethyl group. We have 2 ethyl groups on the amine, and so this could be called dimethylamine. Here we have 3 methyl groups, so we could call it 3 methyl groups, 1, 2, 3 methyl groups. We can call this trimethylamine. A very common way to name these for simple amines. Of course, it won't work for more complex amines. And so we want to fall back on the systematic name, and this is the way you should generally name these. So what you want to do is follow the same steps that we've been using before. Find the largest chain that contains the amine and is attached to the amine. So in this case, the largest chain that contains the amine and is attached to the amine is this one right here. And so this part here has 6 carbons, and the amine group is on the 3rd. We're numbering from left to right here, because if we number left to right, we go 1, 2, 3, and we get to the highest priority amine group at carbon number 3. But if we number right to left, 1, 2, 3, 4, we won't get to it till carbon 4. So we're going to call this 3 because the amine is on carbon number 3, and hex because there are 6 carbons in the parent chain, and because there are no double bonds, otherwise we'd put ene, and then amine because the primary functional group, the highest priority functional group, is the amine. And so that gets us our 3-hexanamine, which goes right at the end of our name. At that point, we've got several different groups here. We've got a couple of chloro groups. So this here is going to give us, right here, this is going to be a 2, 2 dichloro group here. 2 chloros on both on carbon number 2, and then also attached to the nitrogen is an ethyl group and a methyl group. And so the way we label the other groups that are attached to the nitrogen but are not a part of the main chain is we say N with the N locant. So this is telling us they are attached directly to the nitrogen atom but are not the parent chain. So N-ethyl, N-methyl. And at that point now we just have to list them in alphabetical order. The chloro is going to come before the ethyl, which is going to come before the methyl, because we still follow the alphabetical rule. And so we're going to put the 2,2-dichloro first, separate that from the next group with a dash. Then we put the N-ethyl, again because chloro comes before C comes before E in the alphabet. Then lastly, we're going to put the N-methyl. And again, always separate the numbers and the letters with a dash, and there is a dash also between the N-ethyl and N-methyl and so forth. Finally, we do have one chiral carbon. That chiral carbon is the one with the nitrogen here. And so I'm going to go off to the side here, and I'm going to figure out what the priorities are. So the nitrogen here will have the highest priority with the highest molar mass, so it will be priority number 1. On the dash here, we're going to have a hydrogen, so that's going to be priority number 4. And then in terms of the other priorities, 2 and 4 are both carbons, but the carbon number 2 has 2 chlorines attached and 1 carbon. So these 2 chlorines here and this 1 carbon. And then this carbon number 4 has 1 carbon and 2 hydrogens attached. And so the chlorine here beats the carbon. And so this is going to be number 2, and this one's going to be number 3. And so here we have 1, 2, 3, 1, 2, 3, left-hand turn, S, and we can say just S, since there's only one chiral center here, we can just say S, or we could say 3S. Make sure to put that in parentheses. And so that's how you do the nomenclature of amines. I encourage you to practice on the homework with naming the amines. I assigned the Skill Builder 22.1 for that, along with end of chapter problems a little bit too for some extra practice. Now, in terms of the properties of amines, the N atom here is typically sp3 hybridized, assuming that it's got here, in this case, it's got 3 sigma bonds, 1 lone pair. So X plus, so we have 4 electron pair groups. So that's a steric number here of 4. One of them is a lone pair here. So that gives us a trigonal pyramidal shape. The bond angles are slightly less than 109.5, which would be the normal bond angles because the lone pair takes up a little bit more space than a bond. And so it's about 108. Carbon-nitrogen bonds are about 147 picometers in length. These are slightly shorter than carbon-carbon bonds, slightly longer than carbon-oxygen bonds. This makes sense because as you go left to right on the periodic table, carbon, nitrogen, oxygen, fluorine, these atoms are getting smaller. So smaller atom, carbon is a smaller atom than nitrogen, so it makes a shorter bond. Nitrogen is a smaller atom than carbon, so it makes a shorter bond. Oxygen is an even smaller atom, so it makes an even shorter bond. The question here at the end asks, under what circumstances would the nitrogen be sp2 hybridized? Right? Under what circumstances would the nitrogen be sp2 hybridized? So the nitrogen would be sp2 hybridized, for example, if it were involved in a double bond like this. Here there would be 3 electron pair groups, and there would be 1 lone pair, and so this would be sp2 hybridized. One of these electrons, this pi bond would be composed of 2 unhybridized p orbitals, so they're not going to be hybridized as sp3, and so this would be an example in sp2 hybridized nitrogen. Nitrogen atoms with 3 alkyl groups will also be chiral. The reason why they're chiral is because the lone pair is like its own group here. However, amines are generally not optically active, and the reasoning has to do with the fact that this other group, this 4th group, is a lone pair, and it's not an actual atom. So although they are chiral, they're not optically active. And the reason for this is that the lone pair here are electrons that are moving around, and so we get a rapid interconversion of where those electrons are located. So you can think of this as similar type of like flipped umbrella conversion that occurs in an SN2 reaction, right? So you may recall that in an SN2 reaction, when we have some alkyl halide here, and then the nucleophile comes in and attacks, and the leaving group goes away, we get this flipping of the stereochemistry. And that is true here, but it's just basically like the electrons are jumping positions from one side of the nitrogen atom to the other. And so they can undergo this kind of flip. There is an energy barrier to this, but the energy barrier is small enough that this interconversion occurs quite rapidly, and so you don't have a preserved single stereochemistry, and so you don't see that the rotation of light, plane polarized light occurs in one direction. Instead, you have just a mixture of each of these. You've always got basically a racemic mixture of these two enantiomers, and so their optical activity is going to cancel one another out. In terms of the physical properties of amines, amines with fewer than 5 carbons are typically soluble in water. This is similar to with alcohols as well. Alcohols with 5 or less carbons are generally pretty soluble in water. As you go up to 6, 7 carbons, their solubility begins to rapidly drop off. Once you have like 8 or 9 carbons, they're almost completely insoluble in water, unless you have another alcohol group or another amine. So for every amino group, you're going to have more and more solubility, just like for every hydroxyl group, you'll have more and more solubility. This is going to become really important as we look at biological compounds later on, because you and I are mostly water, and so the number of polar functional groups that can hydrogen bond to water really matters in terms of the solubility. In terms of the boiling points, amines do have hydrogen bonding like alcohols, but that hydrogen bonding is not as strong. And the reason why is because the nitrogen is just not as electronegative as oxygen is. So the nitrogen here will have electronegativity of 3.0. For an oxygen, it's 3.5. So this bond here is significantly more polar, right? This is a more polar bond. Whereas although there are two nitrogens or there are two hydrogens and nitrogen is pulling electron density away from them, it just doesn't have the pulling power that oxygen has. So you can see the result in terms of the relative boiling points. If you have propane here, its boiling point is going to be very low because there are no dipole-dipole forces. It is only London dispersion forces, which are relatively weak for small molecules like this. They can get really big if the molecule gets big, but these are all molecules of about the same size. So we can compare them directly. The boiling point of the propane, very low, negative 42 degrees Celsius. For amines, it's quite good. It's quite high, 17 degrees Celsius. So the ethanamine here will evaporate at room temperature. By the way, when ethanamine does evaporate, it smells quite fishy. That's the smell of it. So when you're smelling fish smell, you're smelling a lot of times a lot of ethanamine. Amines tend to smell fishy. And then alcohols have significantly higher boiling points because their hydrogen bonding is a lot stronger. So this only has London dispersion forces. This has hydrogen bonds, but they're weaker than in alcohols. And this also has hydrogen bonding forces, but stronger ones because of the oxygen atom rather than the nitrogen atom. In terms of comparing the boiling points of amines based on their substitution, it's going to differ significantly based on whether the amine is primary, secondary, or tertiary. If it's primary, the nitrogen is basically more exposed and less sterically hindered, so it can undergo more hydrogen bonding. So you'll see that the hydrogen bonding forces are the strongest. So in terms of hydrogen bond strength, this one's going to be number one with the strongest hydrogen bonds. And then the ethylamine here, and you can see it also has two hydrogens, right? So it can undergo hydrogen bonding. This will have less hydrogen bonding, having less of a hydrogen exposed here. Here, there's no hydrogen bonding because there's no hydrogen attached to nitrogen. So you can see you completely lose that benefit of hydrogen bonding. Although it is a polar molecule, so it's not going to have a boiling point as low as for example, propane, but it will have dipole-dipole forces. As we saw, the nitrogen, the electron density is going to be pulled inwards towards the nitrogen, and so that's going to make the nitrogen area partially negative. And so there's going to be some dipole-dipole forces there, but they aren't going to be as strong as the hydrogen bonding forces, and so you'll get a lower, you're going to get a lower, boiling point here for the triethylamine than you would for the propylamine. As I said, many small molar mass amines have unpleasant odors. They smell fishy. Some of them smell not even just fishy, but extremely bad. So they have common names that represent this. Especially if you have diamines here, diamines make this smell even worse. So diamines are named in the same way as diols. So if we had two alcohols here, we'd call this 1,4-butane diol. Since we have two amines, we call it 1,4-butane diamine. And this is also referred to as putrescine. from the word putrid. It smells terrible. And here this would be 1,4-pentane diamine, which is also called cadaverine, which smells like a cadaver. It smells pretty bad. So amines smell bad. And smaller amines smell fishy. These diamines smell particularly awful. One of the key chemical properties of amines is their basicity. So if we look at triethylamine here, the pKa will be in the upper 30s. So the pKa here is going to be approximately 38. So this is going to be not an acid. In fact, it's better as a base. So it has a lone pair of electrons that can make a bond. So amines work well as a base. And so we can see here what they will generally do is accept a proton. And there we go there. And so here we have a carboxylic acid. So of course the pKa for the carboxylic acid is quite low. pKa for carboxylic acids are around 5, quite low. So this is a much stronger acid than the triethylamine. So this is really going to give up its proton. The triethylamine will take the proton, the lone pair electrons here making that bond, and these electrons being left behind on the oxygen. So this makes our nitrogen have 4 bonds and no lone pairs, giving a positive formal charge. And here the deprotonated carboxyl group here has a negative formal charge too, with the oxygen atom having 3 lone pairs and 1 bond. Now, in terms of the equilibrium here, the carboxylic acid is far more acidic than the protonated amine, and so this equilibrium is going to favor the protonation of the amine quite significantly. You'll have about the difference here is about 6, and so we'll have 10 to the 6th power more of this of what we have on this side. And so this will definitely favor the protonation of the amine. Now here's a variety of pKa values for a number of various ammonium ions, protonated amines. So here we have the pKa of a protonated methylamine at about 10.6. You can see all these protonated amines have a pKa that's somewhere around 10 to 11. Now if we have a more substituted amine here, notice that this varies with a pattern that's kind of hard to discern, I'd say. The trimethylamine having a lower pKa than the diethylamine, for example. But what you can see here is that for the monosubstituted amines, their pKa's tend to all be around, on the 11ish side. When you have a secondary amine here, the pKa's are a little bit higher. When you have the tertiary amine, the pKa for the trimethylamine is about 10, but the tertiary triethylamine is about 11. And this reason here has to do a little bit with the hyperconjugation, having more of the carbon groups here. But you don't have to memorize this pattern. I mean, it's just, I think what you should basically know is that for protonated amines like this, just standard protonated amines without any resonance, their pKa's are going to be around 10 to 11. Okay. Now, if you have a amine though that here has a that has the potential for resonance in the deprotonation, you're going to have a significantly lower pKa. So, for example, a benzylamine here has a pKa that's around 5. So, in the substituted benzylamine, this is because if we analyze their conjugate base here, aniline has significant resonance stabilization of its lone pair due to the fact that it's a benzylamine, and this would continue all the way around. There's quite a few other structures. So if I drew this resonance structure here, and I'm not going to draw all of them, I'll only draw some, but we have now the negative formal charge, the lone pair right there. This nitrogen is now making a double bond, and so it has a positive formal charge with 4 bonds and no lone pairs. And then we can draw the next resonance arrow here. We have an allylic lone pair. Again, this was allylic lone pair. Again, we have allylic lone pair, and this will continue all the way around the ring. So due to the resonance stabilization of the conjugate base, which we know we can evaluate here, we're thinking here about REO. So we apply REO to the conjugate base and say, how well does it stabilize the negative charge? Well, with the benzylamine, it stabilizes the negative charge much more than if you don't have this resonance possibility. And so because the conjugate base stabilizes the negative charge well, that makes the conjugate acid a stronger acid. It produces a more stable product, and so it's more likely to do that. And so we can see that all of these protonated benzylamines will have a pKa of around 5. Now, pyrrole has an even greater, an even lower pKa here. This is a ring that contains a nitrogen atom. The lone pair here is delocalized, being an allylic lone pair. So it is significantly stabilized again due to this resonance, and now the lone pair is within the lone pair is within the aromatic ring. It's an aromatic lone pair, even further stabilizing this, and so you get a very low pKa. Likewise with pyridine, you get a pretty low pKa of around 5. And this is going to be, if you notice the difference here, the reason why is because this lone pair is delocalized. It is, but this lone pair is not delocalized. And the quick way to pick that out is that when you see that nitrogen engaged in a double bond here, it's this is an sp2 hybridized nitrogen, sp2. It's got 3 electron groups. One of them is a lone pair here, but its unhybridized p orbital is tied up in being involved in this aromaticity, and so the pyridine is particularly stable, and so losing the protonation from the pyridine does produce a stable product. So the pKa is quite low, analogous to these benzylamines. However, it's not as low as the pyrrole, because this lone pair here is actually stabilized by resonance and by aromaticity. This lone pair is not. And so it's and that's the difference there in the pKa's. So what's the take-home message? Protonated amines have pKa's around 11. Aryl amines pKa's around 5. Pyrrole, very special, pKa 0 to 1 here. In general, if for solubility, amines with more than 5 carbons are only slightly soluble in water. You can increase the solubility, though, by reacting the amine with an acid, because the acid will protonate the amine and produce an ion. And we know from the past, ions are more soluble in water. So this was, one of the first labs that people do in Chem 212 is, having an insoluble amine, adding acid and watching it dissolve, and then adding base and having it come out of solution. So amines can be extracted from organic impurities by using acid and protonating them. And so just to demonstrate that here, if we have, let's say we have this amine right here, not particularly soluble in water, not soluble. However, if we react with hydrochloric acid, this is going to behave as an amine. It's going to go and it's going to grab the proton here from the acid. And then what we're going to produce for ourselves is a ammonium salt. And so now this nitrogen will have 3 hydrogens attached. It will have 4 bonds and no lone pairs, giving it a positive formal charge, and it will be chloride that is left over here, and that has a negative formal charge. So you get this ionic compound. Ions are far more soluble in water, so this is going to be quite soluble in water, and so we can make an amine soluble by adding acid. This is used extensively in the drug industry. So if you guys have ever seen a drug that says blank 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 ene HCl, next time you look at some kind of pill bottle or something, see if you notice this. what this is saying is that it's been reacted with HCl to produce the soluble ammonium salt, which makes the drug more effective because it will more easily dissolve into your aqueous tissues and bloodstream. So in terms of the pKa's, as I mentioned, so the pKa's of the alkyl amines are around 10 or 11, but the arylamines, these will be less basic due to their lone pair being delocalized. And so again, we have allylic lone pair here, and we get this structure, and then we have allylic lone pair again. And we get this resonance structure. We have allylic lone pair again. We get this resonance structure. And of course, at this point, you'd have allylic lone pair again, and you can get the last resonance structure. And so because of this, because they're less basic, that means their conjugate acids are more acidic. And we saw that the pKa here was about, for the protonated, was about 5, right? For the arylamines, they're less basic than the alkyl amines. As I said, the pKa's here are around 5-ish. If you introduce an electron withdrawing group here, you can further decrease those pKa's. So here, this carbon nitrogen is electron withdrawing, and so we can further reduce those pKa's by further stabilizing the ring. It will decrease the basicity, increase decrease the basicity of this conjugate base, thus increasing the acidity of its conjugate acid. With amide groups are not acidic, as we discussed in the carboxylic acid derivatives chapter, and this is because their lone pair is delocalized due to it being allylic. We have an allylic lone pair in the amide group, and then this nitrogen is a double bond and 2 single bonds, giving it 4 bonds and no lone pairs, which is a positive formal charge here for a nitrogen. The oxygen here having 1 bond and 3 lone pairs gives it a negative charge. And we can see that in terms of if we look at the electron potential map, there's significant electron density around the oxygen, meaning that it kind of spends a lot of time here in this type of configuration where the electrons are spending a lot of time around the oxygen. Thus, they're not really available here to be donated to create a bond to a proton and get protonated. So amides are not very basic at all, as amines are. So amines are basic, amines really aren't. It's not nucleophilic as well because, again, to be nucleophilic, you'll want to be negative and have a lone pair to give up. The amide is not in that case. That lone pair density, that electron density is spread out due to the resonance. Now, at physiological pHs, which is around 7.3, amines are going to exist primarily in their ammonium ion form. And so pH 7.3 is acidic enough to protonate. Basically, if we look at this the pKa here, pKa was around 10, right? The pKa, biological pKa, the pH is around 7.3. These would start to become deprotonated around pH 10, right? When the pH would be around the pKa, you can analyze this using the Henderson-Hasselbalch equation. So the very simple way to analyze this is saying if the pH is equal to the pKa, then that means if pH equals pKa, then that means this whole term must be 0. And this term will be 0 if these are equal. And so the log of 1 is 0. And so if the concentration of the protonated amine here and the conjugate base are equal, that will occur when the pH equals the pKa. So if the pH is lower, that means that we're going to have more of the acid component. If the pH is higher, we'll start to have more of the base component. Since this is more acidic than pH 10, we're going to have about 1,000 times more of the protonated amines than the unprotonated at biological pHs. In terms of the preparations of amines, well, actually, I think at this point I'm going to end the lecture. I think this is a good place to stop. As we move forward, we'll start in this lecture, we talked about the properties of amines, their nomenclature, their physical properties, their chemical properties as a base. As we start the next lecture, we're going to move on to the reactions of amines, and I look forward to having you in the next video. Have a good one.